In Episode 22, Build Robust Security Requirement Traceability from Start, we focus on the simple promise that everything important will be visibly connected from risk to requirement, to design to test, and, finally, to real evidence. When that promise is kept, people can answer hard questions quickly, such as why a control exists, how it was implemented, and whether it was ever actually verified. The fog around who asked for this and did we test that clears, and security work starts to feel less like improvisation and more like a disciplined engineering practice. Good traceability is not about creating one more spreadsheet. It is about creating a shared map of intent and proof. That is the mindset we will build throughout this discussion. The first foundation for that shared map is a consistent set of unique identifiers for risks, controls, and the requirement statements that connect them. A risk might be labeled with an identifier that encodes its category and sequence, while a control or requirement line receives its own stable reference that does not change when the text is refined. These identifiers should be short enough to use in conversation, but stable enough to survive refactoring and system changes. When a developer mentions a particular requirement, the identifier lets everyone else find the same artifact without confusion. Without this disciplined naming, traceability quickly collapses into a tangle of similar phrases and duplicated entries. Once identifiers exist, you can begin creating the bidirectional links that give traceability its real power. A security objective or risk record should link down to the user stories, design records, and test cases that claim to address it. In the other direction, each story, design decision, and test should point back to the requirement or risk it supports. These links make it possible to start at the top, asking how a risk is mitigated, or at the bottom, asking why a given test exists, and reach the other end in a few steps. In practical terms, that means a product owner, architect, or auditor can all navigate the same web of connections and see a coherent picture. Trace links become much more trustworthy when they carry context, not just pointers, so it is worth recording assumptions, rationales, and constraints directly within trace records. An assumption might state that a control is only needed in a particular geography or for a specific customer segment. A rationale might explain why one design pattern was chosen over another, such as favoring a simpler control that aligns with existing operations. Constraints might document performance limits, legacy interactions, or regulatory boundaries that shaped the chosen solution. When this context is attached to the trace, someone revisiting the decision months later can understand not only what was chosen, but why it made sense at the time. Security controls do not stand alone. They must be verified to matter. So a good trace model maps each control to concrete verification steps, owners, timelines, and expected artifacts. A control could be associated with recurring test procedures, configuration checks, or monitoring reviews, each with a named owner responsible for execution. Timelines indicate how often these activities should occur, whether on each build, before a release gate, or on a periodic cadence. Expected artifacts might include test reports, screenshots, configuration exports, or monitoring dashboards that show control operation. This mapping turns the abstract idea of control in place into a set of observable activities with named evidence. Design work often resolves several requirements at once, so it is important to capture design decisions that satisfy security requirements along with explicit acceptance criteria. When an architecture document or design ticket describes how data will be encrypted, how access will be segmented, or how logging will be implemented, it should reference the relevant requirement identifiers. At the same time, the trace record should show what conditions must be met for the design to be considered acceptable, such as key lengths, rotation intervals, or specific segregation rules. These acceptance criteria can later be used by testers and assessors to judge whether the implementation truly matches the design intent. In this way, the design layer becomes a bridge between requirements and tests rather than a separate narrative. Testing is where many stakeholders first feel the benefits of traceability, because tying test cases to requirements clarifies what is actually being checked. For each requirement, you want to see a cluster of test cases that cover normal success paths, expected failures, and edge conditions at the boundaries. Positive tests confirm that allowed behavior works as intended, while negative tests confirm that forbidden behavior is blocked or handled safely. Boundary tests probe input limits, rate thresholds, or unusual combinations that might expose weaknesses at the edges of valid ranges. When these test cases are explicitly linked to requirement identifiers, you can quickly see where coverage is strong and where it is missing. As teams start to rely on these links, manual status tracking quickly becomes fragile, so it is wise to automate status rollups that show gaps, blockers, and readiness for release gates. Tooling that pulls information from requirement records, design tickets, and test results can generate views that summarize which requirements are implemented, which are tested, and which still have open issues. These views are particularly useful for release decision meetings, where time is limited and participants need a clear picture of residual risk. Automated rollups also help highlight aging risks that have been recognized but not yet fully addressed. With good automation, traceability moves from a static document to a living dashboard of security progress. Change is a constant in any real project, so maintaining lineage when requirements split, merge, or change across iterations is essential. When a single high-level requirement is broken into several more precise ones, the trace model should show that lineage so that upstream risks and downstream tests do not become disconnected. Likewise, when two overlapping requirements are merged into a clearer statement, their combined history and links should be preserved. Versioning practices, such as recording when a requirement was updated and what changed, help reviewers understand why a link might point to an earlier form. This lineage prevents subtle gaps from emerging when the text evolves but the associated controls and tests are not reassessed. Modern systems rarely rely only on internally built components, which means traceability must include supplier software, services, licenses, and attestations within the same web. A requirement that depends on a third-party library or cloud service should link to the specific component, its version, and any relevant contractual or licensing constraints. Attestations from suppliers, such as security certifications or penetration testing summaries, can also be attached to show how external assurances contribute to meeting requirements. When incidents or vulnerabilities arise in supplier components, this trace model helps teams quickly identify which risks and controls are affected. In effect, your traceability network extends beyond organizational boundaries into the supply chain. When traceability is properly structured, exporting trace views for audits, customer assurance, and regulator demonstrations becomes a straightforward task rather than a scramble. For an auditor, you might generate a view that starts from a control objective and shows the connected requirements, design records, tests, and evidence samples. For a customer security review, you might emphasize high-level risks, the major controls that mitigate them, and the verification summary without exposing all internal artifacts. Regulators may require yet another angle, perhaps focusing on specific data protection or access control requirements. In each case, the underlying trace remains the same. You are simply selecting the most relevant slice to build confidence. To keep the trace network healthy, It must be reviewed regularly rather than left as a one-time setup artifact. Planning sessions provide an opportunity to confirm that new risks and requirements are being integrated with proper identifiers and links. Design reviews can include a quick check that proposed solutions reference the correct requirements and that acceptance criteria are clearly stated. Sprint retrospectives, or similar events, can carve out time to assess whether traces remained accurate through the work just completed and whether any shortcuts were taken. Over time, these small, routine practices help maintain trace completeness without turning it into a large, separate project. By this point, the elements of robust requirement traceability form a coherent pattern that is worth holding in your mind as a single mental model. You start with unique identifiers, then build bidirectional links that connect risks, requirements, stories, designs, and tests. You enrich those links with rationale, assumptions, and constraints, and you map controls to verification steps, owners, and artifacts. You preserve lineage as requirements evolve, extend the trace web to supplier components and attestations, and use automation to surface status for decision makers. Finally, you reuse the same underlying structure to serve audits, customer assurance requests, regulator engagements, and internal planning conversations. That pattern is what turns traceability from documentation overhead into a strategic resilience asset. To close, it is helpful to translate this model into one concrete action you can take soon. Starting a trace matrix for a current or upcoming effort is a practical first step, even if it begins as a simple structured table in your existing tooling. Choose a handful of top priority security requirements, give them stable identifiers, and connect them to the most relevant risks, design elements, and tests you already know. As you do, add at least one acceptance check or expected artifact for each, so that it is clear how success will be recognized. From that modest starting point, you can gradually expand coverage and automation, building a traceability practice that supports both daily engineering work and the most demanding assurance conversations. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.